I will start the second lecture of the 8th week of this course. In this lecture, I will talk a little bit more about Miller planes. We will take the special case of the hexagonal system and what is called the Miller-Bravais indices, and I will also talk about the distance between Miller planes. Okay. And this, as you saw in the last lecture, the Miller planes are Miller indices are used to represent these lattice planes. Okay. We will restrict the discussion to Miller indices for lattice planes in this lecture. We won't talk about Miller indices for directions. Okay. And what I want to show is just give you some more special cases of Miller indices, that is Miller indices for the hexagonal system, and also talk about the spacing between these lattice planes. Okay. So, week 8 lecture 2 will be Miller indices for the hexagonal system and the distance between planes. So, the hexagonal system has a 6-fold symmetry axis. Okay. So, if you look at any hexagonal system, okay, then you essentially have a 6-fold axis of rotation. So, it is characterized by this 6-fold axis of rotation. I am just showing it in a I mean, this is to be treated as perpendicular to the plane of the screen, and you can imagine something else like this. Okay, and you can complete this, and this is the hexagonal system. This is the typical hexagonal system, and you can see that there is a 6-fold axis of symmetry. You can, I will show it by this color. Show this as a dotted line. So now this is a 6-fold axis of rotation, okay, and in such a case, okay, now if you take the unit cell for this, so the unit cell is typically taken as this. So, it will be taken as A1, A2 and C. Okay, so, these are the Miller indices. Okay, I am using A1 and A2, okay, instead of A and B, okay, and that will become clear why I am using A1 and A2, but you can also think of it as A, B and C. Okay. And these are the primitive translation vectors for this cell, or these are the vectors for the unit cell for the and this is usually chosen as the conventional unit cell for this system. Okay. Now, in this case, if we look at let us say we look at this plane. Okay. Now, the Miller index for this plane is 0, 1, 0. Okay. Now, let me look at the Miller index for this plane. Okay. Now, this plane has the Miller index. So, it intersects the A1 axis at 1. So, it is Miller index for the A1 direction is just 1. The A2 axis it intersects at -1. So, it is 1 bar and it does not intersect the c axis. So, it is 0. And let me take one more plane just for completeness. Let me take this plane. This plane, okay, is clearly it is 0, 0, 1. Okay. Now, one of the things that now the hexagonal system has a 6-fold axis of symmetry. Therefore, we expect zero 1 0 surface should be equivalent by symmetry. Okay, is let me write it down explicitly, is equivalent by symmetry to 1 bar 0. And now in the case of the cubic system, we saw how equivalent directions were related by just a permutation of the indices. Okay. But here these two do not have any, the equivalence between these two is not obvious if you look at the indices. Okay. It is clearly we see that these indices are it is not this is not obvious looking at Miller indices. Okay. So, if you look at 0 1 0 and 1 bar 0 for a now they are actually equivalent, okay, by symmetry, but that is not obvious when you look at the Miller indices. Okay. And this is the problem that is addressed by the use of what is called the Miller-Bravais indices. Okay. And this is a HKIL notation. This is also known as the Miller-Bravais indices. Okay. So, instead of just calling it the Miller indices, sometimes it is called the Miller-Bravais indices. Okay. So, the basic idea is the following, that if I let me just look let me assume that the screen is perpendicular to the C plane, okay, and so this hexagonal system will look like a perfect hexagon here. Okay, I am just showing the and we had the lattice translation vectors A1 and A2. C is perpendicular to the screen and I am not showing it. Okay. Now, if I imagine taking a third A3, okay, then if I can see that A1 plus A2 plus A3 is equal to 0. So, they clearly add up to 0. Okay. So, now the idea of this Miller-Bravais indices is to introduce an extra index along A3. Okay. So, just as you had Miller index along A1 and A2, now we introduce an extra Miller index along A3. Okay. Now, clearly this is not independent. Okay. In fact, it is called redundant. Redundant means it is not really needed. Okay. It is an extra index which is not necessary to describe the plane. Okay. However, it is still useful. So, we use a notation H K I L, okay. And because of this relation we have I is equal to minus H plus K. Okay. Okay. So, now how does this help? Okay. So, let us go back to what we had in the last slide. So, we had the 0 1 0 and the 1 1 bar 0. Okay. So, now the 0 1 0 goes to 0 1 1 bar, I is equal to minus H plus K. Now, H is 0, K is 1. So, minus of H plus K is minus 1. So, 0 1 1 bar 0. Okay. So, that is 1 bar. Then the next case we had 1 1 bar 0, okay. And in this case I is equal to minus of H plus K, H plus K is 0. So, I is equal to 0. So, it has 1 1 bar 0 0, okay. And so the Miller-Bravais indices okay. So, you see this Miller-Bravais indices are actually 4 indices instead of 3. Okay. The fourth one is reserved for the C axis, okay. And the other 3 are reserved for A1, A2 and A3, and you can see that these two equivalent directions, they are represented by a permutation of these numbers. Okay. So, you can permute these indices between each other and you will still get equivalent directions. So, in other words H K I L is equivalent to I K H L, which is also equivalent to I H K L and so on. Okay. So, you can take up to you can do the 6 permutations of these and you will get equivalent directions. So, these are equivalent by symmetry. Okay. And what we see is that introducing this redundant index allows you to immediately identify equivalent directions. Okay. So, this is called the Miller-Bravais indices and this is very commonly used for hexagonal systems. Okay. Now, next let us look at these family of lattice planes and let us ask what is the distance between lattice planes. First, let us consider a cubic system. So, in a cubic system, the cubic system you have A is equal to AI, B is equal to AJ, C is equal to AK. Okay. So, these are the 3 primitive translation vectors. They all have the same length and they just point in different directions. They point in perpendicular directions. So, now if you have Miller index H, if you have a family of planes given by HKL. So, this is a set of parallel planes. Okay, then you can ask what is the distance between these planes. Okay. If you have let us say one plane, then you can ask what is the distance, what is the perpendicular distance between these two planes. Okay. And this turns out to be a fairly important quantity, okay. And I am not going to do the derivation of this, okay. It is fairly simple geometry, but in the case of in the case of cubic, okay, you can just show that it is equal to, you can write this relation 1 over d square, d is distance between the planes, is equal to h square plus k square plus l square divided by a square. Okay. In other words, d is equal to a divided by square root of h square plus k square plus l square. So, that is the distance between these set of parallel planes. Okay. Again I am not going to do this derivation. So, basically if you had a plane, so what it means is that planes with small values of HKL, okay, have largest distance. Okay, so they are the ones that have the largest distance between them, and these are also referred to as high symmetry planes. Okay, so those planes that have small values of HKL, they are referred to as high symmetry planes, and they have the largest interplanar distance. Okay. So, if you give a Miller index like so 1 0 0, 1 1 1 1 0, 1 1 1, these are all the high symmetry planes, and if you have something like you know, so on the other hand, if you have something like let us say 1 7 8, okay, this is not a high symmetry plane, this is a low symmetry plane. Okay, and the reason this is called these are called high symmetry planes and low symmetry planes is that if you look at that plane, okay, you will see that in that plane there are some of these symmetry elements which are there in the overall crystal. Okay. I will not discuss too much in detail about that, but basically you keep in mind that small values of HKL, okay, they have the largest distance, and these are referred to as high symmetry planes. Okay. Now, what about the case when you have let us say an orthorhombic system. Now, in this case the formula just changes a little bit. So, 1 over d square is equal to h square over a square plus k square over b square plus l square over c square. Okay. And this is another very well used formula. Okay. Now, notice that again you have a, b, c perpendicular to each other. Okay. So, you can just use something like a Pythagoras rule. Okay. So, they are all perpendicular to each other, only their lengths are different. Okay. And in this case you can calculate the distance using this formula. Okay. Now, so far so good, and it is these formulae are fairly easy to derive, at least for cubic and orthorhombic systems. Okay. But we can also derive them for the more general case. Okay. And but in that case the expression becomes fairly complicated. Okay. So, let me just write the general expression. Okay, I won't expect you to derive it or remember it, but basically the general expression for distance between lattice planes. Now you have A, B, C, alpha, beta, gamma. So you could have all these, okay, and the general expression, okay, in order to write the general expression, okay, we first write the volume of the unit cell. Okay. Now, this, as we said, it is given by A dot B cross C, the scalar triple product, and this can be written as A B C 1 minus cos square alpha minus cos square beta minus cos square gamma plus 2 cos alpha cos beta cos gamma. So, it is a product of all these and this whole thing raised to half. Okay, so, this is cos alpha cos beta cos. So, here what I mean is a product of all these, cos alpha into cos beta into cos gamma. Okay. So, it is this whole thing raised to half, and so this is the volume of the cell, okay, of the unit cell formed by these three primitive translation vectors, okay, and or these three lattice translation vectors, and now the distance between planes, between HKL planes can be written in the following way. H square divided by V by BC sin alpha plus K square divided by V over AC sin beta square plus L square divided by V over AB sin gamma square plus 2 HKL ABC, and you have C by L cos alpha cos beta minus cos gamma plus A by H cos beta cos gamma minus cos alpha. Okay, and you can see that there is a symmetry in each of the terms, B by K cos alpha cos gamma minus cos beta. Okay. So, actually you can see that you have the one type of term which comes from this H square divided by V by BC sin alpha for and then once you have this, you can just switch H to K, switch B and C to A and C and alpha to beta, okay, and you will get this, and similarly again by switching things you can get this. And then you have this additional term, this is HKL into ABC, and you have this expression, but again each of these expressions is this, it looks very similar. Okay. For example, you have A by H cos beta cos gamma minus cos alpha. So, similarly you have B by K cos alpha cos gamma minus cos beta. So, this is the general expression for distance between lattice planes, and this expression, okay, even though it looks a little big, okay, it is extremely useful, okay, and this is probably the, I mean, the fact that you can write such a general expression allows you to index X-ray diffraction patterns, okay, that tells you about it gives a lot of information about the structure. We will see this when we discuss X-ray diffraction. So, I will conclude this lecture here. Okay. So, here and with this I will conclude the discussions on Miller indices. We can see that these we have seen the Miller indices for planes, and so what we have seen is that Miller index is a very useful way to characterize planes, okay, and to characterize these lattice planes, and we can also calculate the distance between these lattice planes. Okay. And it is this distance between lattice planes that will be probed by powder X-ray diffraction, and this will be the topic of the next few lectures. Thank you.